Hi. So can we start? I'm Julian. I've come to talk about Memcheck versus optimizing compilers. I'm kind of the de facto maintainer of Memcheck, so I spend a lot of time dealing with problems caused by optimizing compilers, which seem to have got worse over the years, or better at optimizing, but more problematic. So this is something of a bit mathematical talk. I'll show a bit about how Memcheck tracks definedness of stuff, and then I'll talk a bit about some problems. So come in. So basically Memcheck, which you may have used, it basically does two things. It determines whether you're reading and writing in the wrong place, or checks the location of all memory accesses. And that's relatively simple because there's not much ambiguity about whether this place is okay place to read or write or not. You know where the bounds of the heap blocks are. But the other thing that it does is to check whether branches and some other program constructions, basically addresses, depend on undefined data. And that's considerably more difficult because you have to follow undefinedness through the whole program to do this, or through the whole process. Shall I pause? Please. Welcome. Yeah, it's kind of crazy. Can I continue? I continue. So for a tool like Memcheck, we put a lot of effort into making sure that the false positive rate is very low, and in particular the false positive rate for undefined value errors. And I think it's sort of somewhat known for that. So when it comes along and says this is, undefined value used here, it's likely to be correct. This is important because lots of false positives make tools less useful for developers. So back in the good old days of 2005, that was all fine. We had most stuff under control. Occasionally you got false positives, but we could get rid of them. 10 years later, we have Clang 3 and GCC 5 and their successors generating all sorts of problems, some of which are not easy to get rid of. So what I want to show you is some basics about definedness tracking. I'm sorry if it's a bit mathematical. Some problems where we have some solutions, and some problems where actually I have no idea what to do, and it's actually, I think it's quite serious. So here's some maths. You can throw things at me if it's too boring. Oh, here's some basics, sorry. So what Memcheck does to cut out all the intermediate stuff is for literally every bit of the state in your process, that's all the memory and all the registers, it has a second bit, a shadow bit, which follows it around everywhere and tells you whether that bit is defined or undefined. And we use I could use this. We use we use 1 to encode undefined and 0 to encode defined, which sounds a bit perhaps not what you'd expect, but it makes the code generation more efficient. So when we come to actually calculate a value from operands like r equals x plus y, when the program does that, then Memcheck has these shadow values of the same size, which I write as x hash and y hash. So literally if x is 16 bits, then x hash is also going to be a 16-bit thing containing shadow bits. And then we want to compute somehow the definedness of the result, r hash. And so by doing this, it tries to follow definedness through all the arithmetic in the program. And when it gets to like an if, or the use of a value for a memory address, or for a couple of other obscure things, it actually checks whether the value is defined, and it generates an error at that point if it's not. So we wrote this all down quite nicely in this paper, which you can look at if you like this kind of stuff. So here is some basic building blocks, which I'll talk about a bit. Sorry, it's all a bit mathy. So our most important building block is U if U, which means undefined if either argument is undefined. So this takes two, how can you say, vectors of definedness bits, here's an example, and produces another vector. So I'm writing a 4-bit vector dddu, meaning 3 bits saying defined and the fourth one undefined. And we combine it with this one here, ddud. So we get 2 bits which are defined and then 2 bits which are undefined. And because defined is 0 and undefined is 1, that means you can just implement it using a standard OR operation. So then there's a dual operation, d if d means defined if either argument is defined, which we'll use much more rarely. Here's another one called left, I called it left, which finds the rightmost undefined bit in the word and then propagates it leftwards, like that. So it finds this bit here, and then you get all of the bits above it are undefined. So we'll see how that gets used. Bizarrely, you can implement that by negation and ORing. There's a lot of bit twiddling tricks. And the last building block is this thing called pessimistic cast, which takes some vector of definedness bits and produces a vector of definedness bits of some different size. And the idea is that if all of the input bits are defined, then all of the output bits are undefined. But if any of the input bits are undefined, then the whole output is undefined. So that's why it's sort of pessimistic, because anything bad that comes in produces complete badness at the result. So the most important case is when we want to take a bunch of bits and check if any of them is undefined, so that we'll just be p-casting down to a single bit there. And there's even more weird bit twiddling which implements this. So Memcheck spends half its time, well, a large amount of its time running all these sort of weird low-level arithmetic operations. That's what you're actually waiting for. So let's see some simple case. So let's instrument addition. So we're going to take some simple operation in the original program, some, r is x plus y. I mean integer addition here as well. And the simplest thing we could say is if we find a bit in either input operand which is undefined, then the resulting output bit is also going to be undefined. So we can use u if u on the definedness input to produce the output. But that's actually kind of too simplistic, right? Because when you add things, then you get this carry which can go arbitrarily far up the word towards the most significant bit. So we need to actually do something about carry propagation. And so the simple thing is to assume the worst case, that the carry is going to come all the way along the word upwards. And this is my most significant bits here. They're here for you. So we're going to assume in particular that, you're going to get propagation all the way along. So we're going to pull in our left building block that we just saw there. So we first merge the two arguments, getting a single word, and then we propagate badness left. And that's actually really cheap to co-generate. It's a couple of moves, a couple of ORs, and a negation. And that works pretty well. But it's excessively conservative because this defined zeros actually stop the propagation. And unfortunately, LLVM has come to know this fact. And so what LLVM does is sometimes when it wants to set a bit in a word, it doesn't do it by ORing, it does it by addition. And this causes false errors because LLVM knows that, I'm not exactly sure of the details, but that knows that there's some strategically placed 0 bits in one of the arguments which will stop the carries propagating upwards, even in the presence of undefined values. So that's a bummer, and we need to do something more expensive sometimes. So it's like, thanks, LLVM. Yeah. So I enjoy the improved performance of the code, but I don't like having to deal with these problems. So let me move on to instrumenting something which is actually even simpler sounding, which is and or. So here we go again. Same kind of deal. Program does bitwise and of two operands. And so we're going to say, well, obviously, the result is undefined if either input bit is undefined for all input bits. So we're going to use u if u again. But the problem is that this is actually excessively simplistic. And obviously, if you take any bit which is undefined and AND it with a defined 0 bit, then the result is 0. So I say it matters because compilers endlessly do things like pull a big piece of like 32 bits out of memory, even though some of them are undefined, and then use AND to mask out the undefined bits. And we need, AND with a mask. And we need to be able to track that exactly. So at this point, I don't want to get too much into the maths, but what I want to show is that we're going to take our initial naive simplistic term, and then we're going to improve it by using defined if defined, and we're going to generate two sort of improvement terms from the operands, which tell you where you have defined zeros in the input. So one thing that you can take from this is that to instrument an AND operation, you need to know not only the definedness of the inputs, but you also need to know the actual input values now. So you have 4 inputs, and it's beginning to turn into a big complicated piece of code. You have a bunch of ands and ors and nots and stuff. So it's kind of suboptimal, but you have to do it. Same deal for or, when you turn everything upside down, swap the ones and zeros. But the good news is that this is an exact interpretation. It gives you exactly the right results, and that's a fact which we will come back to shortly. So I want to show you one more example which has actually become a big problem recently, which sounds so harmless, and it's instrumenting integer equality on not equality. So the program is going to compute a single bit result by comparing two integers, like whatever size. Sounds harmless, right? So we're going to use pcast u if u again to merge them sort of in parallel. Then we're going to use pcast to merge all the bits down to a single bit. So the result of this is that we say the result is going to be undefined if any input bit is undefined. And it's like, okay, sounds reasonable. And actually, this worked pretty well for about 10 years until about 2015. But actually, it don't work no more because Clang 3 came along. And then I think GCC picks up its bad habits from Clang. So that's my theory anyway. So what Clang will do nowadays, imagine that we have this structure which contains two 16-bit ints, and we want to compare, both of them and then do something. So what Clang will do, and probably what GCC will do now as well, is just generate a 32-bit load for both fields of the structure, and then compare, it as a single thing. So if in the original source code, if this is not true, then it never looks at that because of the C semantics. But here, it's going to look at it anyway. So we wind up doing a comparison on partially uninitialized data. And I'm thinking, I want to kill myself. No, it's not that bad. So what can we do about this? So you observe that the program actually still works right when the compiler compiles it like this, so it must actually be correct. The question is to make the instrumentation actually match reality now. So what is the key observation? The key observation is that if you need to find two corresponding bits in the input, here I write x 0 and 1, and if they are different and they're both defined, then we know that the whole two words here are not the same, right? So we know that these two words are not the same, regardless of the fact that we don't know what all these x's are, because the 1 and 0 make it so. In this case, the two zeros don't help us because we still need to look at the x's to determine whether they're different. Yeah.
It says result is undefined if they are defined but different. But the line below says it's defined if they're defined but different.
Ah, you're right. It's a bug.
Okay.
Yes, yes. Result is defined. Ah, I checked it so carefully this morning too. Well, thank you. So yes, we can fix up the scheme like we did before. So we're going to take our naive version, which is u if u, again, but this time we're going to generate some improving term which kind of improves the result, makes it more defined, exactly by looking for bit pairs like this, which they're different but the same. So it gets, I'm not expecting you to understand this, but the point is it gets complicated fast and it gets expensive fast. So, you know, we have an improver term and then we have this weird function which actually does a kind of optimistic cast. It's the parallel to the pessimistic cast we talked about earlier. You can look at the gory details in the code base if you really want to see this stuff. But the real point about it is that this is expensive to do. It's like going to be 10 instructions now in the code, in the generated code instead of 3 or 4. It's actually difficult to prove right. So I had my prop here somewhere. So I have this whole bundle of bits of paper, which is my proof attempts to prove. This is several pages, not just one. Attempts to prove that this transformation actually is correct, and it's generally ungood. Also, this function ocast, which is a kind of a shortcut way of saying if any input is defined, then the whole result is defined. I had a less efficient version before, and this weird version is generated by the GNU Super Optimizer, so that actually improves the performance a lot, but it makes it even more obscure. So the question is, well, that's kind of rubbish. Can we do anything better? So we can kind of do something better. So we cannot necessarily do it faster, but at least there's a way to prove whether these interpretations are correct or not. And what you can see from sort of basic Boolean algebra is that you can write any function, any combinatorial logic function, you know, this is like Boolean algebra 101, using just and, or, and not on individual bits, right? Or also XOR, because it's kind of convenient here, so we can take some subset of these three. And like I said in my previous slide, for and or we have an exact interpretation, exact instrumentation, and the same is true for not and XOR. So that means that if we first take any operation we want to instrument, write it in terms of single bits, and then apply our instrumentation scheme to that, then we will have something which is actually correct, even if it's not optimal. And then what you need to do is prove that that's the same as what you're generating code with. So my prop here is my proof that for equality. So
and then you put that through the optimizer, and it comes up with.
No. No, so I wanted to say first, this is just what you do for a 3-bit input, 3-bit equality. So you expand it like this, and then you expand it with these NOT and XORs, and then you apply the interpretation to this. And what you try and do, or what I tried to do, is prove that the instrumentation of this is the same as what I actually implemented, which is no fun, but it's doable.
Wouldn't UBSAN have to do the same?
Well, I think OPSAN actually, I don't know exactly how it works, but I think it probably has a simpler instrumentation scheme that just determines, observes when you're reading uninitialized memory. But I don't know if it actually tracks in this much detail. But I would say I do not know how OPSAN works. I actually was talking about MSAN, so OPSAN is something a bit different as well, maybe. Anyways.
Well, for this proof, could you not just use an SMT solver to do this for you?
Please, thank you for volunteering. It's like, yes, you probably could if I knew about that stuff and I had enough time to do it. I mean, yes, it would be good. But there's also a lot of other things, like we have an expensive interpretation for add and subtract, which is exact, and I would like to prove that that is correct. And not only prove it's correct, but maybe find a faster way to do it, because it's slow. So anyway, enough about bit twiddling. I wanted to actually sort of show what the current status more or less is. So in the current trunk, which will be in 3.14, which is not released, we have exact interpretation of add and subtract, which is actually driven by an analysis. So when of the block being instrumented. So when it knows that we don't actually care about or whether in certain circumstances it can show that the cheap and expensive interpretations are going to produce the same result, and so it uses a cheap whenever it can, and we do exact integer equality by default now. So that actually produced a performance loss of about 3 to 4% in Memcheck, but it's like, well, it's either that or just have all these false positives occurring to everybody who uses, Clang optimized code and now GCC7 optimized code. And it's like, no, don't want to go there, because having a low false positive rate, I think, is really important. Sort of for the record, we have long since implemented and/or and not and shifts and some other stuff widening exactly, because all the basic bit twiddling stuff that gets done. Most other stuff, including floating point, is just approximated on the basis that any input that's undefined causes the whole output to be undefined, and that's sort of good enough. So the result is it kind of works fairly well for GCC7 and Clang 5. It also works for Rust C compiled code, because that's for me a priority, because that's a priority for Mozilla, and Rust is a big deal in Mozilla now. Some somewhat open questions. I'm still dealing with three-way comparisons for the power instruction set. How they do comparisons is different. Like I said, I'd like add and subtract and equality and not equality to be faster. And so maybe some clever person can figure out how to do this. We could also be somewhat clever about the instrumentation, because you can kind of see opportunities for optimization where you do all this exact tracking of bits, but then at the end of this chain of computation, all you care about is, are any of them undefined or not? And it might be possible in that case to actually do the whole sequence more cheaply. So that sort of pertains to this old game called abstract interpretation. Yeah.
Will it be possible to delay this evaluation of the definedness? For example, for the equality, not equality, you can have a cheaper equality test.
Yeah.
After taking the branch.
Some kind of speculative thing, maybe.
Delayed, I will say, like you wait until you take the branch to check the definedness of the condition.
Maybe. I don't know. So I just wanted to end by showing two open questions, one of which is not a big deal and the other of which is a big deal. So the one that's not a big deal is about exclusive OR. So exclusive OR is kind of weird, and it doesn't really fit in the framework properly, because if you take any value and put it into both arguments of an exclusive OR operation, and you get 0 as a result, and it doesn't matter what those values were. What actually matters is the identity of the values. So if I have a value here, which I put in one side of my exclusive OR, and I send the other values sort of all around the place, behind the moon and back into the other side of the exclusive OR, then you get you get a defined value. And so we do not have anything that tracks identity of the values. I don't even know how to do it. For some simple cases like XORing two register, the same register together twice to produce 0, which is a standard idiom, then it's fine. But in some more complicated cases like bit field assignments from the Visual Studio compiler, then you get problems. So yes, we try and rewrite it on the fly, but it's sort of difficult and limited. But that's not the big deal. So a much more serious problem is that Clang 4 started violating a basic assumption about Memcheck. So Memcheck has always assumed that every conditional branch you make has importance in the final result of the program. But that's not actually true anymore, because what both compilers will do is to, in certain circumstances, compile A and B in the C semantics as if it was B and A. So this is pretty hard to get your head around. But if it's always the case that A is false whenever B is undefined, then you can switch these around and you still get the same result, because you're doing either if false and undefined, which is false, and here you're doing if undefined and false. So it's either true and false or false and false. But the problem is this conditional branch is now on undefined data. And I think that some fancy kind of interprocedural analysis that Clang does in this kind of situation, if it analyzes the behavior of this function we're calling, it will do that transformation. So I actually have no idea what to do about this. And it's like, it produces false positives on optimized Clang code and optimized Rust code, and to some extent optimized GCC code, generated code. You think, well, maybe this machine code analysis game has its limitations and this is sort of the end of the road, or maybe we need some new framework to do this, but I do not know how to fix this. Yeah, that's how I felt too.
I understand that it is valid to do in that case, but is it an accident, or is there a reason why switching the conditions around?
Oh, you mean does it have a performance benefit?
Yes.
You'd have to ask a GCC or Clang person that. I cannot tell you that. I do not know the reason for it. I wish they wouldn't do it, but it.
Want to mess with you.
They succeeded.
But maybe it's just a transformation that doesn't really matter, but makes something simpler for the compiler. But if it doesn't really, maybe we can convince the compilers.
Yeah, that would be nice. I know almost nothing about this. The only thing I know is that I have the impression this was something to do with some transformation which split basic blocks into pieces or something.
No.
Yeah.
And why would that be difficult to solve? It's not much different from your end on bits if you know one is 0, so you don't care about the other. here you will probably have a series of jumps.
So we come to a jump, a
Yeah,
conditional
You
branch.
come to jump, but if there are two jumps, the second one is defined 0, and there's no change to state of the program, no change to anything between those jumps.
Yeah.
Then the first one doesn't matter.
Well, so I was considering that, and I thinking maybe I can fix it up, but then I kind of got lost in the details. So maybe it's fixable. I mean, it would be great if it was fixable. Anyway, let me just say, in conclusion, we saw some simple cases. We saw some cases where we needed to have a better precision. We saw a bunch of complexity and expense in the implementation, which I don't like, but I don't know how to really avoid it. It would be nice to have some mathematicians to grind away at these problems and produce shorter sequences for common stuff like addition and equality. Because, you know, I don't like the performance losses. And thank you. Any questions?
Do you have a way to use the fast ones that we currently have and fall back on the slow one if it says that's undefined?
Yeah, so some kind of speculative instrumentation. Yeah, so that would be doable, but that, you know, that's a whole framework, you know, JIT runtime framework decision to produce a piece of code which you can execute and say then, oh, we don't like that, we're going to do this one instead.
Which is adding them as an outline path.
Yeah. I haven't considered, well, I have thought about that, but, you know, that's a lot of engineering.
Run your instrumentarium on your own instrumentarium.
Well, Philippe runs Valgrind on Valgrind before every release to find any badness.
Yeah.
But yeah, we do.
And you see regressions or...
Well, not really. We're actually very careful to avoid uninitialized values. But yeah, we do this sometimes.
Yeah.
Mainly the problem is the sort of two levels of virtual machine you get. That's the real tricky part.
Yeah, especially if you have like the older stuff and the newer stuff,
Yeah.
which have completely different different ways of doing that because the optimization is different.
Yeah.
That maybe some old stuff can help the new stuff.
Well, yeah.
Say like, Because I was looking at it like, yeah, you use compilers to make compilers.
Yeah.
You use analyzers to improve your analyzers.
Yeah, the real thing we find when we do these runs is stuff like using memory that's been freed and stuff like this.
Oh.
Yeah. But usually Philip basically finds almost nothing. We're very paranoid about pre-initializing everything anyway. I think our heap allocator, internal heap allocator, probably zeroes out memory it gives out. So that only really leaves you with uninitialized values on the stack to deal with.
What's the most sensible way of contacting you guys?